Welcome back from the quiz. In this section of low vision, we're going to focus primarily on telescopes. Let's get started. All right, everyone, let's talk about telescopes. So remember, we kind of talked about telescopes a little bit in geometrical optics, right? We talked a little bit there, we kind of planted the seed there, and then we're going to kind of hammer that home here in this video section. So remember when we talked about telescopes before, the big picture with telescopes is that we want parallel light coming into a telescope, right? And we want parallel light leaving a telescope, right? That's the ideal situation for a telescope, right? Parallel light entering a telescope, parallel light leaving a telescope. All right, guys, there's going to be three key equations here that we're going to use for telescopes. They're all going to be here in the text. Let's look in the text, right? So first equation is going to be your tube length equation, right? So tube length is going to be the focal length of the objective plus the focal length of the ocular, right? That's going to give you the ideal tube length based on the power of your objective lens and the power of your ocular lens so that you have parallel light coming in and parallel light leaving, right? So that's going to be your tube length. That's equation number one. Equation number two and number three are going to be two different ways that we can calculate magnification for a telescope, right? So look in your text, you guys will see that one way to do that is going to be the negative, don't forget the negative sign, the power of the ocular over the power of the objective, right? And so right out the side of that, don't forget the minus sign, okay? Don't forget the minus sign. So power of the ocular over the power of the objective, number two. And then number three is going to be your magnification based on the diameter of the entrance pupil and the exit pupil, and it's going to be dent over dex, right? So magnification is diameter of the entrance pupil over the diameter of the exit pupil, dent over dex, right? So dent over dex. Very good, guys. You guys will see that here in the text. We talked about exit pupil and entrance pupil a little bit more in geometrical optics whenever we talked about those as well. One other thing I want to mention to you guys see this box here in the text. Sometimes there's a shorthand notation for telescopes that you have just A by B, like AXB. Right? What that stands for, as you guys see in the text, the first number is going to be the magnification. The second one is going to be the diameter of the entrance pupil. So let's look at the example 5.35, right? It says, what is the size of the exit pupil for a 5 by 45 telescope? So that's this example. I just want to show you that in the text, right? So what that means is it's a 5x telescope, right, with a 45 millimeter objective lens, okay? So that's what that tells you. That's what that tells you in your in that that notation. So, all right, guys, why don't you guys work example 3.5? I'll go to the whiteboard and we'll work it together. All right, everyone. So for solving example 5.35, the key there is just remembering what 5 by 45 means, right? So I wanted to go over that and kind of hit that pretty hard so you guys will remember that and see that as we move forward on the quiz questions in case it comes up on boards, right? So the 5x, just remember that 5x, that's the magnification, right? 5x, we normally think of things in x's, right? 5x is magnification. And remember the other one, the 45, is going to be the diameter of your objective lens, right? The diameter of the objective lens. And we'll talk a little bit more about that here in just a second. So in this case, you're going to have the diameter of the entrance of the objective lens. Remember that the diameter of your entrance pupil, right? So the entrance pupil is the image of the aperture stop for a telescope, which is the objective lens. So the diameter of the entrance pupil, or the entrance pupil itself, is just going to be the image of the objective lens made by all the lenses in front of it. And remember, for a normal telescope, there are no lenses in front of the objective lens. So that means that the entrance pupil is at the objective lens, right? And we're going to draw that on a picture here in just a second when we talk about Keplerian and Galilean telescopes. So if that's kind of like, oh yeah, I remember that, Ryan, don't worry about that. We're going to draw it on a picture here in just a minute. But so the big picture here is that whenever they give you a 45 millimeter objective lens for a telescope, you can think, okay, that's the diameter of the entrance pupil, right? So whenever we work this equation around, magnification equals dent over dex, right? We can use that to get the diameter of the x pupil, which is going to be 9 millimeters, right? So the key that'll unlock this, number one, is 5x by 45, magnification, and the diameter of the objective lens. And then to remember that the diameter of the entrance pupil is the same as the diameter of the objective lens in normal telescopes. Great job, guys. Let's go on to talk about Keplerian telescopes. Remember, a Keplerian telescope is going to be one that's going to have a positive objective power, and it's also going to have a positive ocular power, right? So both of them are plus lenses, right? Both of them are plus lenses. So remember, with any kind of telescope, what we want parallel light coming into a telescope, parallel light leaving a telescope. Now, because your objective lens is a plus lens, it's going to converge light, right? So as you notice, inside a Keplerian telescope, right, light is going to cross, right? So inside of the Keplerian telescope, light is going to cross. Okay, we're going to use that in a second as we go through and highlight some things. Now, this is just kind of review what we talked about in geometrical optics, but just kind of hitting it again, and we just talked about it a second ago. Remember, the aperture stop for any kind of system is what limits the amount of light to get into that system, right? Remember, we talked about light limiter, right, is the aperture stop. So what is going to be the aperture stop for a telescope? it's going to be the size of your objective lens, right? So that's going to be our aperture stop, right? So AS, aperture stop, right? Now, whenever we think about the entrance pupil, right, we kind of referenced a second ago. Remember, the entrance pupil is going to be the image of the aperture stop formed by all the lenses in front of it, right? And for a Keplerian telescope, there's not going to be any lenses in front of it. So that means that your entrance pupil, right, is also going to be at your objective lens, right? So that's why the size of the entrance pupil is going to be the size of your objective lens. All right, Job. Now, whenever we talk about the exit pupil, right, for a telescope, the exit pupil is going to be the image of the aperture stop formed by the lens behind it, right? So if we went through and calculated this out and found where the exit pupil for a Keplerian telescope is going to be, because the ocular lens is going to be a positive value, right? What's going to happen is if you start here on the objective lens, right, where your aperture stop is at, and you work your way through the ocular lens, what's going to happen is you're going to have light come to a focus here behind the telescope. So that's why you get an exit pupil that's going to be behind the telescope, right, in a Keplerian telescope, right? So key points here, remember, aperture stop, entrance pupil, objective lens. Exit pupil is located outside the telescope in free space, right, behind the ocular lens. Very good, guys. So there's going to be 6 key points we want to highlight here in the text, right? And I hope this picture will kind of help illustrate why these 6 points make some sense to you, right? So first one is going to be, we already talked about, you see that in the first line there with Keplerian. Remember, it's the objective and the ocular lens are both positive, right? So remember K+, right? Remember talking about K+, right? So both the objective and ocular lens are positive. All right, now going down to that next bullet point, number 2 is going to be the final image by the telescope is going to be magnified and inverted, right? Now look at the picture. It makes sense that you have an inverted image, right? Because light is going to cross inside the telescope, right? So number 2, magnified and inverted, right? Now go down to the bottom of that bullet point. It says this leads to a longer tube length, right? That's and a greater weight. That's number 3, right? So Keplerian telescopes compared to Galilean telescopes, right, have a longer tube length and have greater weight. They weigh more, right? Now, number 4, the exit pupil for a Keplerian telescope is located outside the telescope, right? So that's going to be number 4. So where is the exit pupil for a Keplerian? It's located outside the telescope behind the ocular lens, right? Now, why is that important? Because you get the largest field of view whenever you put your eye at the exit pupil. So since we can actually put our eye at the exit pupil for a Keplerian telescope, number 5 is this allows for a larger field of view, right? Because the exit pupil is outside the telescope and we can align our eye with more closely with that exit pupil. So key point there, larger field of view with a Keplerian telescope. And the why behind it? Because the exit pupil is located outside the telescope. Very good. And then lastly, the exit pupil is pretty small. So number 6, your images appear to be dim, right? Images appear to be dim. So that's going to be your 6 key points there, right? So you get dim images. All right, so now here's a picture for a Galilean telescope. Remember, a Galilean telescope, a little bit different. The objective lens is positive, right? So for both types, Galilean and Keplerian, objective is positive. But for a Galilean, the ocular is going to be a minus lens, right? So if the objective is still a positive lens and the objective size is still going to be our aperture stop, right? It's still going to be what limits the amount of light to get into a Galilean telescope, right? And because there's no lenses in front of the telescope, right, our entrance pupil, right, is still going to be located, right, at our objective lens, right? But now, because the ocular lens is a negative lens, it's going to diverge light. So if we were to try and figure out where our exit pupil would be at, right, that's the image of the aperture stop formed by the lens behind it. So we would think of the aperture stop as the object, right? And so what we would do is we would use our tube length as our little l, our object distance. So we would have light going away, right, from the objective lens, right? And it would be diverging as it went into this minus ocular lens, which is going to further diverge the light, right? And that is in effect going to make our exit pupil here inside the telescope, all right? Right? So our exit pupil is going to be here inside the telescope, right? So Galilean telescope, key point, exit pupil is going to be inside the telescope because it's a minus ocular lens. A minus ocular lens. All right, guys. So let's talk about a couple of topics here. There's going to be 6 points I want to highlight here as well for Galilean telescopes. So number 1 is going to be objective lens is going to be positive, right? And the ocular lens is going to be negative, right? We already talked about that. That's going to be your number 1 key point. Number 2 is you're going to get a a real image number 2 is going to be that you're going to get an upright and magnified image, right? So number 2 is you're going to get an upright and magnified image, right? And so you guys can see that inside this telescope, right, light is not going to cross like it did in the Keplerian telescope, so your image is going to be an upright image, okay? So upright image and magnified, number 2. All right, number 3 is because you have an objective lens and an ocular lens, you have two of them that are opposite in power. What's going to happen is that's going to allow a Galilean telescope to be a shorter tube length, right, or smaller tube length, and it's going to be a more lightweight telescope, right? So that's going to be in that next bullet point there. You're going to highlight the tube length of a Galilean telescope is going to be smaller and more lightweight, right, compared to Keplerian telescopes. All right, the next one is going to be, number 4 is going to be our exit pupil, right? It's going to be, our exit pupil is going to be located inside the telescope, right? So that's going to be, exit pupil is going to be inside the telescope, right? It's going to be number 4. So number 5 is you're going to have a smaller field of view, because remember we said the closer we can get to the exit pupil, the larger the field of view is. Well, the ocular lens is going to block us from being able to get to the exit pupil in a Galilean telescope. So that's going to make it where we have a smaller field of view compared to a Keplerian telescope. Now the exit pupil, number 6, the exit pupil is going to be larger, so that's going to result in a brighter image, right? So comparing to Keplerians, right, Galileans is going to have a larger and brighter image. Okay, so larger and brighter image, number 6. All right, guys, so as I'm going through and studying Keplerian and Galilean telescopes, these 6 points for each that we highlighted, to me, this would be a natural, like, multiple response area that I would try to focus in on studying this. So that's kind of how I would attack, these pages. I would think, okay, what kind of multiple response question could be given? And we say, hey, which of the following 3 characteristics would be characteristic, or which of the following 3 would be a characteristic of a Galilean telescope? And you have to kind of go through those and pick out the ones there that would be a Galilean compared to Keplerian. So that's kind of how I would attack those. Hopefully these pictures helped out with that. Now let's move on and kind of use some of our equations. I've got 2 examples I want to work before we get done with this video section, right? So let's go through example 5.36. It says a telescope has a plus 20 objective lens and a minus 50 ocular lens, right? It says what magnification and type of telescope is it? What is the tube length of the telescope? So I want you guys to work that example and then we'll come back and work it together. So whenever we look at solving example 5.36, first question, what kind of telescope is this? Yeah, it's going to be a Galilean telescope, right? You guys all identified that, right? You have a plus objective lens, minus ocular lens. It's going to be a Galilean telescope. So what's our magnification equation? Remember, it's the power of the ocular over the power of the objective. Don't forget the minus sign, right? Don't forget the minus sign. So you're going to take minus and minus 50 over plus 20. That's going to give you a plus 2.5x, which makes sense, right? Remember, just kind of an overview real quick. Remember when we have a plus, right, in front of a magnification, that means it's going to be an upright image, right? So you have a plus in front of a magnification, it's going to be an upright image. If we have a minus in front of a magnification value, that's going to be an inverted image, right? So we got a plus 2.5. That makes sense because we know that Galilean telescopes have an upright image, right? An upright image, so we got a good answer there. 2.5 is greater than 1, so just kind of going through and talking about that. Remember, with magnification, if it's greater than 1, it means you're going to have magnification. If it's less than 1, you're going to have minification, right? So we're going to have a magnified image, which is what we should have with a telescope, right? So we get an upright, magnified image. That all looks good from our example. But if you forget that minus sign, right, you're going to get a minus 2.5, and that's going to give you a wrong answer, right? So don't forget the minus sign. Don't forget the minus sign. All right, guys, let's talk about the second step of this problem. All right, so how do we calculate the tube length? Remember, that's the first of those equations that we talked about. So your tube length is going to be the objective focal length plus the ocular focal length. So to find your objective focal length, just take 1 over 20. It gives you 0.05 meters or 5 centimeters. Probably easier to work in centimeters here, but you can do whichever one you want. 1 over negative 50 is going to give you negative 0.02 meters or negative 2 centimeters. So now you're going to take 5 plus negative 2, and you're going to get 3 centimeters, right, as your tube length for your Galilean telescope. All right, guys, good job dominating that example. Let's move on and go through example 5.37. So 5.37 says a patient is using the same 2.5 Galilean telescope from the previous example to view an object 25 centimeters away. How far apart should the lenses be set in order for the patient to view the object clearly through the telescope? Now, before you guys work this example, and then we'll break and we'll come back and work it together. Remember, we said that we want a telescope to have parallel light to come in and parallel light to leave, right? So now if we use this telescope, instead of trying to look at something at distance, now we're trying to look at something up close, right, at 25 centimeters, what's going to happen? Instead of having parallel light coming into the telescope, right, now we're going to have divergent light coming into the telescope, right? So what we have to do is we're going to have to adjust the tube length, right, so that even though we have divergent light going into the telescope, light will leave that telescope parallel. All right, guys, why don't you guys get on example 5.37? We'll come back together and work it together. All right, guys, so in this example 5.37, remember we've got light that's now not going to be parallel as it's coming into a telescope, right? It's going to be divergent, right? So we've got our object is here located. I've got a picture here, right? It's 25 centimeters in front of the objective lens. So I'm going to convert that, go ahead and convert that to meters. So negative 0.25 meters, right? And that's going to be our object location, right? So I'll go ahead and put a little L in there. You can also put a little U in there if you guys want to. That'll be a negative 0.25 meters, right? So what we're going to essentially have to do, right, is that we're going to have to do kind of a geometrical optics modification of this telescope to figure out, okay, we know the objective power is plus 20, but because we have an object not in infinity coming in, we have an object that's going to be diverging as it's going into that lens, we're not going to have light converging the same as if we had parallel light. It's going to be different, right? So it's going to effectively change the power of our objective lens. So we have to figure out what is that new effective power of the objective lens, and then we can use that lens power's focal length to calculate this new tube length that we need to have so that we can have parallel light leaving a telescope. So I'm going to show this, I'm going to walk you through this one in case it's a little bit confusing to you. But just kind of, like I said, we're going to use this kind of like a geometrical optics modification. So the power of that objective lens is plus 20. So we think about what is going to be the divergence of light as it enters that objective lens, right? That's going to be 1 over that negative 2.5, which is going to give us negative 4 diopters, right? So negative 4 diopters. So as light is hitting this plus 20 lens, it's going to have negative 4 divergence, okay? Good, so now what we can use is the general divergence equation, right? It's that L prime equals F plus L, or you could also use V equals F plus U, right? Or, V equals P plus U, right? So V equals P plus U, or V equals D plus U, whichever one you guys like to use, right? But the whole point there is that if you take the power of the lens, that plus 20 for the objective lens, and you add in the divergence of light hitting that lens, minus 4, you get a divergence of light leaving that lens of plus 16. So what that means is that the effective new power of that objective lens is no longer 20, right? The effective new power of that lens now is plus 16. Okay? So now we essentially have a Galilean telescope with an objective power of a net objective power of plus 16 and an ocular power of minus 50, right? And so now we can use our tube length equation, right, to be able to figure out what would be the tube length to be able to make it where light will leave that ocular lens parallel, right? So we just take, put a D in there, right? You just take 1 over 16, right? That's the effective new power of our objective lens, plus 1 over negative 50, right? So that's going to be our power of our ocular lens because its effective power is not going to change, right? So what we do now is we have, that'll give us our values here that you'll see, and we end up getting a 4.25 centimeters in terms of a tube length that we need to be able to modify our Galilean telescope. So now we can actually have parallel light leaving the telescope whenever we have an object that is located 25 centimeters in front of the telescope. All right. So whenever you guys are working these problems, they're going to work very similar every time, right? If you have an object in front of a telescope and they ask you what tube length do you need to make to be able to make it where you can have parallel light leaving the telescope, right? What you need to do is be able to convert that object distance, right, into its divergence, add that to your objective power, and that's going to give you your new effective objective power, right? And then you're just going to take 1 over that new effective power, add that to 1 over the ocular power, and that'll give you your new tube length. All right, guys? Great. Well, we're done with this video section. Go dominate the quiz, and I'll see you on the next video.